Today's talk is on complicated chemists. It's rather dramatic title, but I do think it is kind of encapsulates the idea really well. Like, these problems are complicated and these people are also very, very complicated. So the person that we'll be talking about in particular is Fritz Haber, which I'm sure all of you guys at some point will have come across because of the Haber process, which is kind of drilled into you upteen times in school. And one thing which I think is really interesting is just to have a little bit of background on Fritz Haber himself as a person. So he was born to a Jewish family in Poland, and that's of particular relevance in a bit. And it is pretty much undisputed that he was a chemical genius of his era, and the chemistry which he did quite frankly change the world. But the reason why he did it is interesting and is a major part of what I think they miss in school. So you're kind of taught about the Haber process and taught about why it's important, but you're not really told why he came up with this chemistry and why he was inspired to do it, which is a lot muddier. And he was a German chemist during World War I, and he was deeply, deeply patriotic. His inspirations and his driving force was for Germany to win World War I, which we can feel whichever way we want to about that. And he is also a Nobel laureate, which obviously is kind of the highest accolade in chemistry. So we have to kind of appreciate that the scope of his chemistry was huge. So a little bit of a refresh on the Haber process, which I'm sure everyone is familiar with from GCSE, is essentially the process of taking dinitrogen and reacting it with hydrogen gas to produce ammonia. And on the surface, it doesn't look like a very impressive reaction. It actually looks quite simple. And the only thing of note is that this reaction is reversible, which has a whole set of implications on its own. The other thing which I've written up here, which actually I could get a little... Hopefully you guys can see my pointer now as well. Here we can also see that this reaction is exothermic, which means that in the forwards direction, it releases energy and releases heat because it's predominantly a bond forming process. And one thing which I think is really interesting is that the Haber process was discovered off the back of Le Chatelier's principle. So in the late 1800s, Le Chatelier came out with his principle where he stated that if processes are in a dynamic equilibrium, and we'll talk about what that means in a second, that changing or disturbing the conditions is going to affect the position of that equilibrium. I teach students quite a lot, and one of the things which I've noticed is that people generally are not that happy with the definition of what the position of an equilibrium actually is. So what it means is, imagine we have some reactants and we have some products, right? If the reaction is reversible, well, we're going to have them both coexisting at the same time. The position of an equilibrium is essentially trying to define what the ratio is. So do we have 10% products and 90% reactants? Or do we have 90% reactants and 10% products? It's essentially trying to establish what is the ratio and that mixture. So if we change the conditions, basically what we do is we tip it one way or another. That is essentially the big idea here. And the reason why these are called dynamic equilibriums is to emphasize the point that the molecules are actively converting one way and another. So it's not static, right? It's not like once you formed ammonia, the ammonia stays as ammonia and the nitrogen and hydrogen stay as nitrogen and hydrogen. They are constantly interconverting. And one thing which I think is quite interesting about Le Chatelier's principle is one of the ways I like to explain it to people is almost like a bit of a petty child, right? Imagine you have this really bratty kid and it does he in this case, but they do the exact opposite of what you ask them to. You ask them to sit down, they stand up. You ask them to talk quietly, they speak louder and they start shouting. And that's almost how you can think of these systems that are reversible, right? So one of the ways I like to teach this is using a little acronym called DOF, which is disturbance opposite favor. And I like the word disturbance in particular for Le Chatelier's principle. Imagine you woke up in the middle of the night, or your parents walk into the room and wake you up in the middle of the night. That is a disturbance, right? What is the first thing you do after you are disturbed? Well, you go back to doing what you were doing before, or in other words, in this case, you would go back to sleep, right? And we can almost think of our systems in exactly the same way. If we crank the temperature up, so we disturb it and we increase the temperature, well, it wants to do the exact opposite of that. It wants to bring it back down and therefore will favor the endothermic reaction. So one thing which I think is really interesting in this case is that with Le Chatelier's principle, it established this concept of having compromise conditions, right? It's not as simple as saying we want to use a really, really high temperature or really, really high pressure. We actually have to use a balance. So here we can see really clearly that increasing the temperature actually shifts the equilibrium towards the reactants, which is the opposite of what we want. We want to sell ammonia, we want to produce ammonia, so therefore we want to have the equilibrium as far towards the products as possible. So actually using a lower temperature, as we can see in this graph, enables that. But we also have to remember in the back of our mind, kinetics is a thing, right? The more we lower the temperature, the slower a reaction becomes. It's great if you get a 90% yield, but it can't take you a year to get there. So we really have to use these kind of balance of conditions. And one of the things that Harvard actually was able to be quite successful with is finding the right compromise conditions in order to get a good yield in a reasonable amount of time. And one thing which I think is interesting as well is that, well, why is this reaction so revolutionary? We said this is really revolutionary. We said this is like Nobel Prize winning chemistry. It looks pretty simple, but nitrogen is not a scarce kind of element. It's really, really abundant. About 78% of the Earth's atmosphere is in nitrogen, right? So why is this such a big issue? Why do we need to do this chemistry? Well, nitrogen is really interesting because it's one of those elements that actually forms really, really strong bonds to itself. So nitrogen exists in the air as this triply bonded diatomic molecule. And very few things break this apart. Actually, one of the main sources of finding nitrogen that can actually be used by biological systems is by lightning. So you can think of the amount of energy that is required in order to actually split these nitrogen molecules into reactive compounds. And well, then that begs the question, well, why do we need nitrogen? Well, hopefully some of you guys will be doing biology as well, but very clearly the major components of key biological molecules contain nitrogen. So hopefully you guys can recognize DNA. And the bases in DNA are clearly extremely nitrogen heavy. We have to think about where does that come from, right? And then we also consider amino acids shown here, where amino acids contain this amine group, which is why they are called amino acids, right? So clearly it's really, really important that for biological systems to be able to have this nitrogen. And one thing which is really important is we have to remember that all of the nitrogen that is kind of being used to build up protein, generally when we think about protein, we think, okay, eat a steak or something. But where is the cow getting those amino acids from? Well, it is from plants, right? Which means, okay, well, that begs the question, where do the plants get the nitrogen from? And generally, most plants are not able to kind of fix nitrogen. They're not able to just pull it out of the atmosphere. Some plants have special bacteria which enable them to do this. And they have a symbiotic relationship with those bacteria. But generally speaking, a lot of the nitrogen which we were using in this agriculture was present in the soil. So now we can start to see a problem which is going to arise. If you are continuously planting crops in a kind of mass agriculture way, and the crops are pulling the nitrogen compounds out of the soil, well, it doesn't take a rocket scientist to realize eventually it's going to become depleted, right? You have a restricted commodity, which is these nitrates in the soil, and we are essentially depleting them. And so this is why the Haber process plays a massive, massive role. So the Haber process actually it's estimated to be responsible for about 1 to 2% of the world's consumption, energy consumption. I think that's something equivalent to like the amount of energy that Switzerland uses. Don't quote me on that. And roughly half of the world's population, so about 3.5 to 4 billion people rely on fertilizer that has been produced in part by the Haber process. So we need to understand that this has been massively important in terms of food security and feeding the planet. But it also begs the question, what is the cost of that? I'm in no way, shape, or form suggesting that we should allow people to starve, but we also have to acknowledge at the same time that fertilizers are a massive class of pollutant. So here, if we look at the image on the right, this is kind of something that I'm sure everyone has seen in real life when they walk past a park or a local lake. And essentially what it is an algal bloom. And this is not natural and it's not normal. I think sometimes when we see things in everyday life, we tend to fall under this fallacy that it's normal and it's not a big deal. And one of my favorite chemistry versions of this is like ice floating. But generally, what you learn about in kind of year 7 is that like solids are denser than liquids. Well, solid ice is solid water. So why does it float on water? Something to think about. And if you guys want to ask me about it, you can. But the point is, just because we see something every single day does not mean that it's not anomalous, does not mean that it's normal or natural. And in this case, this is entirely abnormal and it is entirely unnatural. And here what we have on the left is actually a dead zone. So it's the Gulf of Mexico or Gulf of America, depending on your politics. But essentially, what has happened is that these fertilizers, which have been used in kind of mass farming, have been washed by kind of rain. And what ends up happening is a process called eutrophication, where this fertilizer ends up in the waterways and fertilizes algae in the water, right, and causes it to grow at a natural rate. And that causes a couple of things. Well, one thing is that it blocks the sunlight from the plants at the bottom of kind of your river or your lake from getting light, which means they die. And then we need to think about, well, okay, well, when things die, they don't just disappear. There are organisms that come and decompose them and use that matter. Well, those organisms, those bacteria, use oxygen, right? So if we have kind of a massive amount of dead organisms at the bottom of a lake, and then all of a sudden we have this humongous growth of these bacteria that come and break them down, well, again, it's the exact same situation. We're going to have a situation where the oxygen in the water becomes depleted, right? So now our ecosystem can no longer support fish or larger organisms which rely on that oxygen. So it's something worth considering. Although kind of feeding the planet is really, really important, there has been this unintended consequence, which is definitely worth thinking about. But one thing which I think is really interesting is that obviously this is nothing that Fritz Haber could have envisaged and nothing that Fritz Haber would have known at the time. And this is a literal kind of screen grab from his Nobel Prize website. And a lot of people find it really interesting because his biography on the Nobel Prize page is very, I mean, for lack of a better term, washed out of the more unsavory parts of the chemistry that he engaged in. And so obviously he was given the Nobel Prize for the catalytic synthesis of ammonia. And we've established why that was really, really important, despite some of the unintended consequences and side effects. But generally speaking, in school, they don't ever teach you about the other things that he was involved in. And also they don't teach you about, well, why was he trying to make ammonia in the first place? And if anyone has an educated guess, you can put it in the chat and I'd love to know. But otherwise, I'm going to reveal it fairly quickly. And actually, one thing which I think is really interesting about Alfred Nobel is he himself was also a complicated character. When you think about Nobel, you think, oh, the Peace Prize, you think about the science prizes. You don't generally have negative connotations with the name. But again, very few people are aware of why he is famous, why he set up the prizes, and also where did his money come from? Which is a perfectly valid question. He left this kind of grand estate for the advancements of peace and science and later economics, but where did the money actually come from? And actually, you learn about this in A-level chemistry, which is the formation or the nitration of benzene. And for people who aren't too familiar with this, it generally comes up in year 13 chemistry. But I do think it is interesting to just talk about. And so, or one of the key principles of organic chemistry is that generally positive things like to react with negative things. Or in other words, the way we talk about that in terms of chemistry and organic chemistry is that electrophiles like to react with nucleophiles. This is a concept that hopefully you guys have come across. And so benzene is this molecule that you can imagine has almost like 3 double bonds. It's not the best description, but it is one that works. And we can imagine it's this very unsaturated molecule with a lot of electron density in this ring. And so we can imagine that this molecule with a lot of electron density is very strongly attracted to positive things. Or in other words, benzene is nucleophilic and it will react really quite strongly and intensely with electrophiles. So here we can see really clearly that actually we can generate these nitrogen electrophiles by reacting sulfuric acid with nitric acid. And what's quite interesting here is that your nitric acid and your sulfuric acid have a little bit of a kind of battle of the acids. And whichever one is stronger forces the weaker one to act as a base. So obviously in no world would you describe nitric acid as basic, but because sulfuric acid is a better base, essentially what ends up happening is that sulfuric acid gives off a proton, protonates your nitric acid, and then nitric acid decomposes into this NO plus ion and water, right? And so we can imagine that happening. And now this NO plus ion is clearly electron deficient. It is also positive. So it makes sense that our benzene, which is kind of this reservoir of electron density, will want to react with it. And it undergoes a reaction known as electrophilic substitution, because we have an electrophile here and it's being substituted. So one of the hydrogens on our benzene ring is being substituted for nitrogen. And here we can see that it forms a nitrobenzene. And one nice thing about this reaction is we can see that it also kicks out a proton, which means that this reaction is actually catalytic in the fact that sulfuric acid is not depleted throughout the reaction. And so that begs the question, well, kind of how is this relevant? Well, it's relevant in kind of two ways. One is TNT, which is what it says right at the bottom. This is how you make TNT. What TNT stands for is trinitrotoluene. So toluene is kind of the name given, is the kind of the informal name for methyl benzene. And essentially when you triply nitrate toluene, you get this very explosive molecule that is kind of commercially thought of as dynamite. And this is how Alfred Nobel made his money. He invented dynamite and sold it, and was very much in the business of warfare. And obviously dynamite was also used in kind of extraction and demolition, but it was primarily, a lot of his money came from it being used in warfare. And they are not confirmed, but there are rumors that the reason why Alfred Nobel set up the Nobel Prize was because he saw an obituary when his brother died, and obviously it was back in the 1800s, I believe. He saw an obituary where his brother had died, and a French newspaper had mistaken it and thought he had died. And in this obituary, they called him the Angel of Death, where essentially they said, here's a man who's basically responsible for lots and lots of people's deaths with his invention and has made a lot of money from it. So there are people that think that the Nobel Prizes themselves are kind of one of the most successful, like, PR stunt is a bit too dramatic, but essentially it was great kind of image rehabilitation. No one thinks of Alfred Nobel as some kind of mass murderer. When you hear the word Nobel Prize, you think of peace. But this is the origin story. Whether that rumor is confirmed or not, historians still debate. But the fact of the matter is that Nobel made his money from kind of warfare and explosives. But the other thing worth noting here is the compound that's used to make TNT, which obviously is nitric acid. And this happened a couple of years ago. I believe it was in 2020, but I'm not sure if you guys remember, but there was a massive explosion in Beirut. And eventually they figured out what was responsible for it, but it was absolutely huge. Like the radius was about kind of 3 kilometers either way. And it's because there was this ship that had kind of tons of ammonium nitrate on it, which again is a very simple compound to make. You take ammonia and you take nitric acid and it forms this salt, which is ammonium nitrate. Again, really, this is just a reaction where you have a weak base, like ammonia, accepting a proton from a strong acid and forming this salt. And ammonium nitrate was responsible for this explosion because there were absolutely tons and tons of it. So now we have to think about, okay, well, why was Haber trying to make ammonia in the first place? And the uncomfortable truth of the matter was, it was not to feed people, it was not to make fertilizers, it was to make explosives, predominantly. The chemistry itself is obviously kind of neutral, but what the use was intended for was to make explosive. So during World War One, the British and kind of, well, I'm not sure if you call them the Allied forces at the time, but the British essentially cut off Germany's ability to import nitrates from South America. So essentially they had to figure out a way to make them themselves. And that kind of gave birth to the Haber process. And it's worth noting that ammonium nitrate can also be used to make fertilizer, but it is also used to make explosives. And nitric acid is a key component in making TNT. And that is kind of the origin story of a lot of this chemistry. So although the Haber process was really, really kind of fundamental chemistry that's helped feed billions of people across the globe, the intention had nothing to do with fertilizer and feeding people. It had to do predominantly with explosives and winning World War One, which Haber was, again, extremely patriotic. Some might even say too patriotic. But unfortunately, the story doesn't quite end there. because beyond explosives, Haber recognized that there was a need to kind of surprise the enemy and kind of take them, well, by surprise, right? And in doing so, essentially became colloquially known as the father of chemical warfare. He was one of the first people to think that actually chemistry could be used to surprise your enemies on the field um, and um, and essentially gain a tactical advantage. And so he began meticulously researching and weaponizing um, some of these molecules, in particular the halogens, um, for warfare purposes. And he started with bromine and then moved to chlorine. Um, and the one thing which was quite interesting is that bromine is one of the only two elements in the periodic table other than mercury that is a liquid at room temperature. Everything else is either solid or gas. And so he started with bromine, but actually realized that it was quite cold in the fields and that bromine froze really easily at these kind of temperatures that were below room temp. And so basically you realize, okay, well, bromine, not good enough for weaponization. But one of the things that he did notice and that he was kind of engineering into his designs is that he wanted a gas that was denser than air. And if you use kind of very basic physics, right, with something denser in a less dense medium sinks. And so if you think about World War One and World War Two, a lot of the warfare was done in trenches. So essentially, the goal here was to design a gas or employ a gas that when you kind of had it in a artillery on the like in a shell, that the shell would explode, but the gas would be denser and it would sink into the trenches and essentially poison people. And although chlorine was used in World War II quite extensively, but didn't stop here. There wasn't really any synthesis involved here. It was just elemental chlorine and elemental bromine. Here, one thing which is interesting is that he concluded that they really weren't deadly enough, despite being very, very effective. And I think the most horrifying part of this story, at least for me, is that Haber's wife was also a very talented chemist in her own right, named Clara. And she, um, after the first successful deployment of chlorine gas in the field, she was absolutely horrified at what he was using the discipline of chemistry to do. Um, and he did not listen to her at all, and she actually ended up killing herself. Um, and 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 the next day, that didn't deter him at all because he then went to the Russian front to see them deploy the missiles that had this chlorine gas in it. So really, he was very much a man on a mission, but can't really agree with what that mission was. Um, and one of the reasons why he concluded that chlorine gas wasn't actually toxic enough or deadly enough was for a number of reasons. One, it's very clearly visible. Chlorine is a green gas, and so kind of you can imagine that the soldiers would have been able to see it from a distance. The other thing is that it was also water soluble. So one of the ways that soldiers were actually getting around it after the first time they had been gassed with chlorine is by actually taking rags that were soaked in either water, ideally, or under more kind of duress, urine, and covering their mouths with it. So essentially, the logic was that they wouldn't inhale it. Because the way that chlorine gas actually had its toxic effect is that it would react with water and create hydrochloric acid and cause scarring of your lungs. And then essentially fluid would build up in the lungs, and obviously the soldiers would die that way. And so Haber was intensely researching other ways to create these kind of chemical weapons. And the concept of a chemical weapon did not exist in this kind of mass commercial way before World War One. And after World War One, these were declared to be like war crimes to use chemical weapons. And obviously, that it's a bit fanciful thinking that they've been completely outlawed because obviously we know that things still happen today. And so the kind of second generation of chemical weapons that Harvard developed was this compound known as bis 2-chloroethyl sulfide, or in other words, very, very simply, mustard gas, which I'm sure everyone has heard of. And mustard gas in particular the way they synthesized this, the reason why it was called mustard gas is because it had a faint yellow color. In reality, this gas is entirely colorless, but the way that they were making it was slightly impure, which is to be expected for kind of the analytical and kind of purification methods that they had at the time. And one thing which I think is really interesting in this case in particular, and I do have a question that I'm going to ask, is that this molecule on the surface was a massive issue because it caused blisters. So it was kind of a blistering agent, but also the additional effect of this molecule that was kind of not a problem or not as big of a problem with chlorine gas is that this molecule was also a carcinogen. And so I guess my question is if anyone has a reasonable suggestion as to why this molecule is carcinogenic, or what does it mean for a compound to be carcinogenic, right? So if you're being told, oh, there's a molecule, it is carcinogenic, what does that actually mean that it's doing in the body? If anyone has any suggestions, I think it would be great, though I am very happy to explain it to people as well. But I will give you guys a minute to see if anyone has any good suggestions. Yep, so it increases the risk of cancer, but why? What biological effect is it having? What is it interacting with? So for example, what is cancer is essentially the question. I got a good suggestion. Yes, that is a good suggestion. So it interacts with DNA, mutates DNA. Yeah, exactly. So these molecules, essentially anything that is a carcinogen is something that interacts with DNA and essentially causes some kind of change to it. And here, this molecule does indeed interact with DNA. And we'll talk about this a bit more in a little bit because I think this is my favorite part of the story, although that sounds a bit morbid, you'll see why in a second. But Haber designed this entirely to cause damage, right? Entirely to like kill people and to essentially maim them and to be deadlier than chlorine gas. And kind of final bit of Haber's kind of playing around with kind of these deadly gases was actually a gas known as Zyklon A and Zyklon B. And so what's interesting about this is Zyklon A was what Haber actually developed. And it was the hydrogen cyanide-based pesticide. And it is one of the only things that he developed that was not with the intention of mass murder. He developed it as a pesticide to be used to kind of kill pests in fields and essentially prevent crop loss, which on the surface you're like, yeah, that's fine. That arguably sounds quite well innocent, you know, right? But then during World War II, essentially when the Nazis rose to power, what they realized is that Zyklon A could be developed and converted into a gas known as Zyklon B. And Zyklon B was used in gas chambers. And so this is the reason why I mentioned right at the beginning that Haber's background was that he was actually Jewish. And so even though he was long dead at this point before World War II had broken out, the developments that he made were responsible for the death of his own family members in some cases, who were sent to these kind of concentration camps and were essentially gassed with hydrogen cyanide. And the reason why Zyklon A was developed is because the Nazis kind of saw themselves as kind of ethical killers, right? They was like, this is an ethical way to kill people, which is obviously a ludicrous statement. But it was Haber's initial invention that led to the inspiration for the gases that were actually used in kind of Auschwitz. And they're responsible for, again, the death of his own family members. And one thing which I think is particularly interesting is that this chemistry hasn't just remained frozen in time, right? This has been very relevant even recently, even within the UK that you wouldn't have thought. It'd be interesting to know, and you guys can just let me know in the chat if anyone remembers. Granted, you guys might have been a bit young, and it was a couple of years ago. But does anyone remember the poisoning that happened in Salisbury, where it was quite scandalous and quite sensational, where essentially people were being told, or it was revealed that like Russian spies were poisoned using these agents known as Novichok. If anyone does remember, like let me know in the chat and keep an eye on it. Yeah, it'd be interesting to know. I think it was maybe 2017, but I can't remember exactly. And the compounds that they used were these kind of Novichok agents. where we can see here really clearly. Thank you. Thank you, Daisy. One person remembers. It was a massive deal, right? Like people just being poisoned with gases in the street is kind of not normal. Um, and and one thing which I think is really interesting in this case, and again, this is some slight overlap with A-level biology, but essentially we can see here the motif that was responsible for imparting this kind of toxic effect was this kind of uh, phosphorus fluorine bond. And so one thing which was really interesting is last year I was doing some chemistry on greenhouse gases for my master's project. And I promise you, I was not trying to make Novichok or anything like it, but some of the chemicals which I was using contained phosphorus and fluorine, and they were restricted. You could not buy them because they are used to make nerve agent precursors. My project was trying to defluorinate gases which are responsible for global warming. So it was kind of an environmental project. But it was really interesting. And then at that point, I realized, well, okay, well, what are the structures of these nerve agents because the chemicals are restricted? And then obviously I looked them up and it made a lot of sense why I couldn't buy some of the reagents I needed. And so it'd be interesting to see if anyone can piece together how these chemicals actually work. So super quickly, if anyone knows, does anyone know the role of acetylcholine esterase, which is an enzyme? It does come up in A-level biology, but I do think it is quite interesting. If anyone does know, you guys can let me know in the chat. Acetylcholine esterase. It's an enzyme, and it has a very, very important function because I don't know if some of you guys do AQA biology, but one of the things that we had to do when I was doing my A levels, which was granted a while ago now, was write about extra information in off-spec information in an essay right at the end. And this is actually one of the things that I wrote about. So acetylcholine esterase is really important in synaptic transmission. So essentially, when we have kind of one nerve impulse and we have another nerve impulse, and now we have another nerve, gas breaks down acetylcholine. Yeah, there we go. Thank you, Victoria. That's correct. Yeah. And so essentially, its job is to take acetylcholine, which is this neurotransmitter, and take the impulse from one neuron. Acetylcholine travels across the synaptic cleft, which is the gap between your two nerve cells, and then acetylcholine esterase kind of grabs onto that, breaks it down, and then the nerve impulse continues. And it's essentially how nervous impulses are conducted. So I guess my next question is, well, okay, well, if we're inhibiting that enzyme and we're preventing it from working, well, then how does Novichok actually work? How does it essentially kill you? And how does it kill you actually quite quickly? If anyone can try and piece two and two together. So essentially what we're saying is we're inhibiting your ability to transmit nervous impulses. So think about, okay, well, what processes rely on nerve impulses? Which there's one really obvious one. Anyone has any ideas? Heart function is correct. There's another one. Think as basic as you can. Moving. Yes, breathing. So if everyone, obviously I'm not with you guys, but if everyone takes a really deep breath in, tell me what you notice. What do you notice? And then you just breathe out. But what do you actually notice when you take a deep breath in? Yeah, your chest moves. And I think this is really interesting. So the way you actually inhale and exhale is that the muscles in your chest essentially create a pressure difference. So when you inhale, your chest kind of expands and moves upwards because the goal is to lower the pressure inside your thoracic cavity so that air gets sucked in. And when you exhale, well, the opposite happens. We kind of compress down because we're trying to push air back out. So essentially, the whole process of breathing is exploiting pressure differences. And you can only do that if your muscles in your ribs and your diaphragm can contract and relax. And so essentially, the way that Novichok actually ends up kind of having its effect is that it paralyzes you and prevents you from being able to breathe. And then obviously, yes, Victoria, you are absolutely correct. It can also cause you to have a heart attack because your heart obviously needs to pump blood. So any kind of movement. So it is fundamentally a paralytic agent. And the way that it does this is that it forms these really, really strong carbon-fluorine bonds with the enzyme, and it prevents your enzyme substrate complex from forming. And because it is a permanent inhibitor, so some people, again, if you do biology, you'll learn about competitive and non-competitive inhibitors. Because this is essentially a non-competitive inhibitor, acetylcholine cannot bind in the enzyme, and therefore nervous impulses cannot be transmitted. And this is all born out of the chemistry that Fritz Haber developed, right? The concept of developing agents as kind of poisons for warfare was just not a thing pre-World War One. And so Fritz Haber, despite not having created Novichok's himself, played a massive role in inspiring and driving this chemistry to kind of exist. But one of the things which I think is really interesting is that we talked earlier about the fact that mustard gas, so this bis-2-chloroethyl sulfide, is a carcinogen. And what we said was that, okay, well, carcinogen is something that interacts with DNA. But here's a counterpoint. If you have cancer, and we're trying to stop cancerous cells from proliferating. So cancer and chemotherapy is kind of a massive topic which chemists look at a lot. Well, what we're essentially doing when we're trying to create drugs that kill cancer cells is we're trying to develop drugs that interact with DNA. So this is where it's a very confusing concept. And the first time I learned about it, I was like, what on earth do you mean? But every single chemotherapeutic agent is in itself a carcinogen. And this is not me trying to peddle any conspiracies about chemotherapy, but the idea here is that if you are designing drugs to essentially kill cancerous cells, well, then they need to interact with cancerous cells and they need to have some sort of toxic effect. So what distinguishes kind of chemotherapeutic agents from poison is that they are developed to be selective for cancer cells, or as selective as possible. So a drug will not get approved if it does not disproportionately kill cancerous cells over healthy cells. So one of the reasons why your hair falls out when you have chemotherapy is because chemotherapeutic agents are designed to kill rapidly dividing cells, of which your hair cells just generally have a slightly quicker cell cycle. So that's why they kind of are disproportionately targeted. And so what I think was really interesting is that this mustard gas, obviously during World War II, dire times, and during World War I, also dire times, mustard gas was being employed, and soldiers that had leukemia were actually still being forced to go and fight on the front and in the trenches. And what doctors started to notice, and this is, I think, the most bizarre unintended consequence of Fritz Haber's chemistry, is that those soldiers that had leukemia and went and were exposed to mustard gas had better survival rates. So somehow the mustard gas was acting as a chemotherapeutic agent, and it was improving their prognosis. And bearing in mind, at this point in time, there were no kind of like chemotherapeutic agents that had been designed and developed. We knew what cancer was, but we did not necessarily have a drug being like, this drug targets cancer, or this drug has shown to improve the prognosis for people with leukemia. And so what doctors and chemists started to realize is that this drug and this motif was responsible for having some sort of anti-cancer effect. And that developed into a drug, which we can see on the left, on the right, sorry, known as chlorambucil, which is basically the first modern chemotherapeutic agent. And here, I mean, it's a very obvious question, but let me know in the chat, what are the structural similarities between these molecules? What do you guys notice? Yeah, exactly. It has that exact same chain. Actually, if you kind of superimpose them, you know what? I will superimpose them. If you actually superimpose it, they are exactly the same down here, are they not? Right? And so just put that back to where it belongs. So actually what we can see here is that they took this original motif and they realized, okay, you have leukemia, it is not ethical to gas someone with mustard gas, even if it was having some sort of chemotherapeutic effect, because again, there needs to be a large gap between its toxic effects and its toxic side effects and its ability to kill cancerous cells. So essentially, the sulfide was decided it is way, way too toxic, like crazy toxic, right? You cannot treat people with leukemia with mustard gas, obvious. But what they realized is clearly this motif is interacting with DNA in a molecule, so we want to keep that. So they tried to replace the sulfur with a nitrogen, right? Now, obviously, sulfur is in the same group as oxygen, so generally it tends to form two bonds, whereas nitrogen is in group 5, and it forms 3 bonds in order to fill its valence shell. And that is also useful. Now, here we can also see that we have this kind of massive side arm that has been attached. And I'd be really interested to know that, can anyone think of any reasons why we might want to attach this sidearm onto the molecule? Think about, what do we want when we're trying to design drugs? What kind of obstacles do we need to overcome? Yes, Harry, you're absolutely correct. 2 chloroethyl groups. Same. Yeah. But what do you think is the role of this kind of phenyl ring and then that carboxylic acid there? What are we trying to achieve? And actually, what's really interesting is the process of developing these drugs is medicinal chemistry. So you add functional groups and you think, okay, what effect is that going to have? Think simpler, right? So the first thing we talked about is this mustard gas. Well, mustard gas is a gas, as the name suggests, right? Generally speaking, we're not trying to gas people in a hospital. When we think about drugs, we think about taking pills, right? Yeah, there we go. Yeah, that was a good idea. Yeah. So one thing, which is we want it to be kind of solid or liquid, right? And that's exactly correct, because it's a lot easier to administer. So, for example, I could send you home and give you these tablets and say, "Well, this is your chemotherapy." Often, sometimes people have a very sensational view of what chemotherapy is, but it can very much just be a sheet of tablets you have to take. So that is one thing. Yes, it's going to clearly make this either solid or at the very least liquid. I think chlorambucil is actually solid. But what else? What else do we need to think about? So obviously now that this is a solid or it's a tablet, we can ingest it, we can take it in. We need this drug to get into cancer cells. What barriers are there? Literal barriers are there to drugs entering cells? Yeah, you need to pass through a membrane. Exactly correct. And here, again, if people do biology, you'll know a lot more about this. But this is what I actually quite like, despite the fact that I kind of did a chemistry degree. A lot of this kind of fundamental overlap between sciences does crop up. Well, what are membranes made out of? What is the bulk component of membranes? Absolutely correct. Phospholipids, right? Phospholipids are the bulk component of membranes, and they are polar molecules, right? But generally, what we tend to learn about is that molecules which are kind of non-polar, not water soluble, right, don't pass through membranes very, very well, right? And so here, what we actually have is a couple of issues that we need to think about. One, we need this to be able to pass through our membrane. But the other thing that we also need to consider is that we need it to be water soluble, right? If this is insoluble in water, it's not going to be able to dissolve into your blood plasma, and then it's going to be very, very difficult to get it anywhere and to have its chemotherapeutic effect. So these are the things that kind of go into drug design, and these are the things that go into medicinal chemistry. We need to consider like the polarity of our molecule, how we can actually get it into cells, and then can it actually have its desired impact, which obviously in this case is to kill cancer cells. And chlorambucil is still used today as a chemotherapeutic agent. And again, this was a completely unintended side consequence of Fritz Haber's chemistry. And so I would be really, really interested to know, like, where do the scales balance for you guys? On the one hand, kind of if we think about the explosive stuff and the synthesis of ammonia, the intention was very much to make bombs. The intention was very much to win World War One, kill as many people as possible, and make bombs out of that ammonia and those nitrogen-containing compounds. But then on the other hand, he is probably single-handedly responsible for increasing food security for over half of the planet. And without it, likely, one, the world's population would have never been able to support what it is right now, which you could argue is either a good thing or a bad thing. But also there would be a lot more starvation across the planet. So food security is massively gone up, but at the cost of eutrophication and causing these algal blooms and actually releasing some of possibly the worst oceanic pollutants. But then on the other hand, we also need to consider the fact, that the kind of a bit more chemical weapon side of it, right? Well, on the surface, I would have thought, yeah, there's nothing redeemable and nothing good from generating chemical weapons or synthesizing chemical weapons. And obviously, that is not a controversial take. But at the same time, the synthesis of mustard gas quite literally inspired the first modern chemotherapeutic agent. That is a fact, right? Had he not made mustard gas and deployed it on soldiers in World War I and II, right, perhaps it would have taken a lot longer to be able to do the medicinal chemistry that was needed to make chemotherapy agents. And so, I mean, I have no definitive answer for that. And I think the only thing which I think and feel quite strongly about is that schools should give you slightly more the big picture. That yes, it's important to learn the Haber process. It is important. It is world-changing chemistry. But I also think you could be told very quickly a little caveat of like, oh, hey, by the way, he also invented chemical weapons and was responsible for kind of a lot of calamity across the globe. But anyway, I'd be really interested to know, how do the scales balance out for you guys? Do you think Haber did more good than bad net? Or do we think kind of the consequences of his actions were overall more negative than positive? But I definitely think the kind of main takeaway here is science is neither good or bad, right? Your intention could be to do something really quite bad, and yet people can find very good uses for it. And the opposite can also be true. Your intention could be really, really good, but if the wrong person sees it and notices it could be weaponized, or it could be designed in a certain way to cause damage, then that is also very possible. So yeah, floor is open. Let me know in the chat. What do you guys think? And hopefully you guys enjoyed that and now have a little bit more context about Fritz Haber, who is a chemist, so you do learn about in school. And also I'd be really interested to know if any of your teachers did tell you that Fritz Haber was responsible for the synthesis of chemical weapons.